Finding three different representations for nth Fibonacci number. So in this video, we will try to find the nth Fibonacci number using recurrence relation, matrix multiplication, and generating function. All these three are completely different ways, right? And we'll also see that actually third way gives us slightly different like nth Fibonacci number formula, and that's interesting. So let's proceed ahead, right? Okay, so Fibonacci numbers, this is a sequence, right? That it starts with 0 and 1, and then we just add first two numbers to get the third one. 1 plus 0 is 1. Again, we add like last and the second last number. 1 and 1, 2. 2 and 1, 3. 3 and 2, 5. 5 and 3, 8. 8 and 5, 13. 13 and 5, 21. 34. 34, and then 55, and then 89, and then 144, and so on, right? These are the Fibonacci numbers, and these are denoted by f sub 0, f sub 1, f sub 2, f sub 3, f sub 4, f sub 5, f sub 6, and so on, right? So goal of this video would be to find a formula for the nth Fibonacci number, right? So yeah, so it will be some function of n, and then if we substitute n as, let's say, 6, we get 8. If we substitute n as 5, we get 5. Yeah, so that's the goal. So first of all, we are going to use recurrence relation because this one is the easiest one, right? And see how it actually gives us the formula. So we here see that the recurrence relation between the Fibonacci number is that f sub n is actually the sum of the previous two Fibonacci numbers, right? So this is the recurrence relation, right? And how do we solve recurrence relation? We just assume a solution of the form rho to the power n, right? We just assume a solution of this form, right? And what we do is, and then we try to substitute it in the recurrence relation, and then try to solve for rho. Rho is some number. From there, we get rho to the power n is equals to rho to the power n minus 1 plus rho to the power n minus 2, right? And that gives us rho square is equals to rho plus 1, which gives us rho square minus rho minus 1 equals to 0. And then that gives us rho is equals to minus b plus minus square root of b is negative 1. So b square minus 4a, c is negative 1 by 2 times a is 1. So this becomes 1 plus minus, this is square root of 5 by 2, right? So here, rho can either be 1 plus root 5 by 2 or 1 minus root 5 by 2, right? And for both of those rho to the power n actually satisfies this recurrence relation, right? So yeah, so we see that both like some constant times 1 plus root 5 by 2 to the power n, and some constant times 1 minus root 5 by 2 to the power n satisfy the recurrence. Right? And now, since these two are solutions by superposition principle, also C1 1 plus root 5 by 2 to the power n plus C2 1 minus root 5 by 2 to the power n also satisfies the recurrence, right? And also it can be verified that this is actually the general solution. And so that's why the general solution will be in this form, right? C1 this thing plus C2 in this thing. Now, this is just general solution to recurrence, this reconciliation, right? But we also have initial conditions. I mean, these two criteria that define the sequence. So we also want to satisfy the fact that f sub 0 is 0 and f sub 1 is 1. And to satisfy this, we just make substitutions and try to solve for C1 and C2. So if we substitute n as 0, we get 0 is equals to C1 times 1 plus C2 times 1, which is C1 plus C2. And using the second, this F1 equals to 1, this gives us 1 is equals to C1 times 1 plus root 5 by 2 plus C2 times 1 minus root 5 by 2, right? Now, since we already have C1 plus C2 is 0, we know that C1 is equals to negative C2, right? Or also, C2 is equals to negative C1, right? So if we use that, we have 1 is equals to C1, 1 plus root 5 by 2, and then C2 is negative C1, 1 minus root 5 by 2, which gives us C1 times 1 plus root 5 by 2 minus 1 minus root 5 by 2. So that gives us C1 times, this is just root 5, right? This is 1. So we get C1 as 1 by root 5. So that means C2 will be negative 1 by root 5, right? So these two constants make sure that our initial condition is satisfied, that these two initial conditions. And so now substituting them, we have the general formula for Fn as 1 by root 5, right? And then this is 1 plus, sorry, yeah, and then 1 plus root 5 by 2 to the power n, and then minus 1 by root 5, 1 minus root 5 by 2 to the power n, right? So now we can actually take 1 by root 5 common. That gives us 1 plus root 5 by 2 to the power n minus 1 minus root 5 by 2 to the power n. And this is our nth Fibonacci number formula. Even though this has roots, the roots mainly, we got this we got the square roots mainly because the fact that we had to satisfy the reconciliation, and that gives us rho in this form, right? But again, we found CR and CD such that our initial conditions were these two, and if this recurrence is satisfied, we just get Fibonacci number. So it doesn't really matter the fact that the roots are here. If you try to substitute n as 0, you get 0. Substitute n as 1, you get 1. If you substitute n as 2, you get 1. If you substitute n as 3, you get 2. You can check that in your calculator. So this is the first form for the nth Fibonacci number that we get using recurrence relation, right? Now let's try to find it using matrix multiplication. Okay, so let's try to find using matrix multiplication. We'll try to use the fact that we can actually find the nth power of a matrix using eigenvalues and eigenvectors, right? So that thing will be helpful. So first of all, let's try to create like matrix relation between like previous and the recent Fibonacci numbers, like so that we can actually find nth power, and that's one. So we actually want a relation between like Fibonacci numbers in previous time step and recent time step, right? So since there are two, I mean, for matrix we at least need like a vector, right? At least with 2 entries. We can have 1 or 3 entries as well. So let's say I want to have fn minus 1. So let's say fn plus 1 fn, right? It doesn't really matter. In the same vector over here. Then we want to relate these two. Sorry. Vectors here, like let's make them one step down in time, right? fn minus 1. Okay. We want to relate them. So fn plus 1 can be found as sum of these two, right? So 1, 1. And fn, we can just use this fn to get this fn. So 1, 0. So in this way, our like the first vector, first element will be fn plus fn minus 1, which is just fn plus 1, and next one will just be fn. So it works, right? So yeah, so the fact that now we have established this relation, now we can find the n power of matrix. So first of all, notice that, okay, so let me just show you that. Okay, let me show you one step. So again, I can write fn minus 1 as the same matrix, right? With fn minus 1, fn minus 2. The same relation, right? So this way, notice that I can continue this until this vector reaches f1, f0, right? So when it does that, we will have 1110 to the power n times f1 f0, right? Just to make sure that we are right, so you can notice that when the power is 1, the subscript is n over here, sum is n plus 1. So also over here, when power is n, the subscript is 1, so n plus 1. So yeah, that thing is conserved, and that's why you can verify. Okay, so now we have established this reason, right? So now the fact that we can actually find the n power of matrix, that will help us solve with this. To find the n power of matrix, we know how to do it, right? So what we do is we first find uh, its eigenvalues, lambda 1 and lambda 2, and the corresponding eigenvectors b1 and b2. And once we have that, we know that the nth power of this matrix will just be, first of all, the matrix of eigenvectors, right? And then the matrix with eigenvalues, but eigenvalues will be raised to nth power, right? And then the matrix of eigenvectors inverse, right? So we know that this will be the nth power. So let's try to find the eigenvalues and eigenvectors first. It's easy to find eigenvalues. What we do is just the determinant of this matrix minus lambda times identity matrix, and make sure that this determinant is 0, right? So from there we get 1 minus lambda, 1 minus lambda is equals to 0. So that gives us 1 minus lambda square minus 1 square is equals to 0, which gives us 1. Am I in right direction? No, I'm not right direction. This is actually 0 minus lambda. I'm sorry. See, I can catch errors. That's a good thing about me, right? Okay, so now this becomes 1 minus lambda minus 1 square is equals to 0. This is minus lambda plus lambda square minus 1 equals to 0. Notice that we actually have same equation, just like while solving the recurrence relation, right? That's not really anything coincidental, that's obvious. Now lambda will be same thing, right? 1 plus minus square root pi by 2. This is also actually golden ratio, but yeah, let's not go to that. Now we have these two eigen values, right? Lambda 1 is equals to 1 plus root 5 by 2. Lambda 2 is equals to 1 minus root 5 by 2. So now that we have the eigenvalues, we can find eigenvectors using the fact that these eigenvalues are defined as just scaling the eigenvectors, right? So lambda 1, let's say it's 1 plus root 5 by 2. So the eigenvector of 1 plus root 5 by 2 will be such that it will just scale the eigenvector by that number, right? So let's write eigenvector as x1, x2, and we'll solve for x1 and x2, okay? x1, x2. So yeah, from this, we see that the equations that need to be satisfied is x1 plus x2 is equals to 1 plus root 5 by 2 x1, right? If we take x1 to other side, this becomes, what will it become? 1 minus root 5 by 2 x1 plus x2 is equals to 0, right? Similarly, the other equation will be x1 is equals to 1 plus root 5 by 2 x2, right? The second equation from the second line. From the first line, this is the equation from the first line. Okay, so now this becomes x1 minus 1 plus root 5 by 2 x2 is equals to 0, right? Now if we use the fact that what can I actually use here? Okay, notice that let's try to solve one of them, and it easily happens that the another is automatically solved. So to solve the first equation, what we can choose is, we can choose x1 to be, this is not minus sign, okay? We can choose x1 to be 2 by 1 minus root 5 and x2 to be negative 1, right? Because then the first one is just 1 and this negative 1, that's 0, right? You can actually verify that this satisfies the second one too. You can actually verify that it's a work for you. So that means the solution, and also like not just these, even if you multiply this by any t, that will still be a solution, right? But we can just take a simplest solution. So we can take x1, x2 as this one, 2 by 1 minus root 5 negative 1, right? Similarly, if you try to find the eigenvalue for the other case when this 1110 and let's say y1 y2 is 1 minus root 5 by 2 x1 x2, you should be able to verify that its eigenvector, sorry, not x1 x2, y1 y2, we can find in similar way. That will just be 2 by 1 plus root 5 times negative 1. So now that we know the two eigenvalues, sorry, two eigenvectors corresponding to 1 plus root 5 by 2 and corresponding to 1 minus root 5 by 2 eigenvalues, right? So now we can write our like general solution, right? So now we will have fn plus 1 fn as the product of this will be first of all the eigenvectors, which is 2 by 1 minus root 5 negative 1, 2 by 1 plus root 5 negative 1 times this will be 1 plus root 5 by 2 to the power n 0 0 1 minus root 5 by 2 to the power, and notice that the first column will corresponds to the first column, right? Because these two are each other's eigenvalue and eigenvector. Second column corresponding to second column, right? And also at the end, we also need to have the inverse of our matrix of eigenvectors to 1 plus root 5 minus 1 to the power n. And also we will have here fn, sorry, f1 f0, right? Okay, so now we know that f1 is actually 1 and f0 is actually 0, right? So if we substitute those values over here and carry out the multiplication, right? So we will have fn plus 1 fn. The multiplication is on you because we already know this vector. We know this vector too. Oh wait, this is not n. This is actually inverse. I'm sorry. This is inverse, okay? Yeah, because I already said that it should be inverse over here, right? Yeah, so yeah, this is inverse. Okay, now we already know this vector. We can find the inverse easily, right? We also know this matrix. We know this matrix. So if we carry out the multiplication, you will get this as something in numerator. Maybe, probably, you will just get 1 plus root 5. 1 plus root 5 by 2 to the power n plus 1 minus 1 minus root 5 by 2 to the power n plus 1. Something like this, right? Yeah. And in the second column, you will get 1 by root 5, 1 plus root 5 by 2 to the power n, minus 1 minus root 5 by 2 to the power n. And yeah, so from here, we can actually find that fn is the same formula, right? So yeah, it turns out the matrix multiplication way will just give you the same formula. And it's a bit tedious to multiply all of these, right? But it works. Now the last way is using generating function, and we'll actually get different answer this time. So let's see how we can actually find the formula using generating function. So first of all, our goal is to be able to evaluate this sum, right? From 0 to infinity of fn x to the power n. And if we have this generating function, and then later on we can try to find fn. So how do we find this, right? So okay, let's see how we can find this. So actually this sum will be, we know that f of 0 is just 0, right? 0 x to the power 0 plus 1 x to the power 1 plus 1 x to the power 2 plus 2x cubed plus 3x to the power 4 plus 5x to the power 5 and then 8x to the power 6 and 13x to the power 7 and so on, right? If I multiply both sides by x, and there's a reason I'm doing this, you will see in some time. If I multiply both sides by x, this will now be 0x to the power 1 plus 1x squared plus 1x cubed plus 2x to the power 4 plus 3x to the power 5 plus 5x to the power 6 plus 8x to the power 7, so on. If you again multiply this by x, so wait a second, you will have you have a miracle like you will have miracle in some time. So this is 0x square plus 1x cube plus 1x to the power 4 plus 2x to the power 5 plus 3x to the power 6 plus 5x to the power 7 plus 8x to the power 8 and so on, right? Now, notice that if you subtract these two from the first expression, what you will get is you will have sum from n equals to 0 to infinity fn x to the power n, right? And then 1 minus x square, right? So this will be equal to, okay, let me show you something now. We know that Fibonacci numbers have like fn is equals to fn is equals to fn minus 1 plus fn minus 2, right? Now if we subtract this n minus 1 and n minus 2, this will just be 0, right? The same thing's happening here. So here, notice that uh, 3x to the power 4 cancels with 2x to the power 4 and 1x to the power 4 because these two are subtracted, right? We are just trying to subtract these two from the first one, right? So yeah, similarly, 5x to the power 5 cancels with 3x to the power 5 and 2x to the power 5. 8x to the power 6 cancels with 5x to the power 6 and 3x to the power 6. 13x to the power 7 cancels with 8 and 5. And then this 21 cancels with 13 and 8, right? So all of these are cancelled. Similarly, 2x cube with cancelled with 1x and 1x cube, right? Because all of these two are just subtracting. And similarly, 1x square cancels with 1x square and 0x square, right? So and then these two are just zeroed, so they cancel by themselves. So what's left is just x, right? Just x. So from here, we finally have the generating function for Fibonacci number. Fn x to the power n is just x by 1 minus x square. But now the question is, how can this generating function be actually be used to find the Fibonacci number? So the way is, we will try to express this thing over here, this polynomial rational function over here, also in the form of sum from n equals to infinity some number times x to the power x. And when we have expressed in this form, we know that these two should be equal, right? So that's the way we are going to deal with it. And now to break in that form, we will actually need to break it in some, let's say, geometric series form, right? Maybe some two fractions. And then we can use geometric series to get in the required form. So let's to break that again. This is quadratic, so we should try to factorize this, right? Factorize, we're going to use complete square method. First of all, complete the square, and then we're going to do something. So if I take minus common, we will have x square plus x minus 1, right? And this becomes x square plus x plus 1/4 minus 1/4, so minus 5/4, right? So this becomes x by negative, this is x plus half square minus root 5 by 2 square, right? So that becomes x by root 5 by 2 square minus x plus half square, right? So this becomes x by root 5 by 2 plus x plus half, and then root 5 by 2 minus x minus half, right? So again, this becomes x by root 5 plus 1 by 2 plus x root 5 minus 1 by 2 minus x, right? Okay, so now we have this. We should not try to break into partial fractions, right? Because then only then we can use geometric series formula and then get x to the power n and such thing, right? So to break, it's not that hard actually. Okay, let's see. It should not be that hard. So let's try to see. What if, okay, in the numerator, let's say if we just have these two numbers getting subtracted, right? And then let's see what that gives us. And then, okay, let's say the denominator should, let's it be as it is, right? Now, if those numbers are subtracted, what will we have in numerator? In numerator, we will have half plus half 1, x plus x 2x. So we have 1 plus 2x. Is that it? Yeah. Uh, 1 plus 2x. So that means now if we divide our numerator by half, what will we have now? So it was 1 plus 2x earlier, so it's x plus half now, right? And now, after we do this, if we subtract half now, then we just have x, right? Okay, so yeah, this makes sense. We just have half now. But now, guys, let me use something simpler. But now, if I break into partial fractions, the second time is trouble for me because there's this half here. Guys, let me use some simpler method. What I will do is I will just use cover up method. Cover up method is way easier. This could also have done, but there was half over there, and that just increases the problem. Yeah. So let me do the cover up method. So yeah, in cover up method, I will just write these two fractions, right? And then what I will do is, first of all, for its numerator, we know that this thing is 0 when x is negative of root 5 plus 1 by 2, right? So what I do is, over here, I substitute x as that value, negative of root 5 plus 1 by 2, in this expression, just by covering up the thing that we made 0. So that gives me, that gives me negative of root 5 plus 1 by 2, right? That makes it 0, by root 5 minus 1 by 2 minus plus root 5 plus 1 by 2, right? Okay. Similarly, this is 0 if x is root 5 minus 1 by 2. So I will cover this up and substitute on other axis, right? Root 5 minus 1 by 2 divided by root 5 plus 1 by 2 plus root 5 minus 1 by 2. Okay. Now this gives me, in denominator, now I will just have 1, because this is 2 root 5 by 2, so that means 1 by root 5. And then over here, in numerator, I have negative of root 5 plus 1 by 2, and then root 5 plus 1 by 2 plus x. Over here, this is root 5 minus 1 by 2, which is root 5 minus 1 by 2 minus x, right? So now let's try the geometric series, but for that, first of all, we need to reduce this into a different form. Let me write the second term first. I will just divide both numerator and denominator by root 5 minus 1 by 2, which gives me 1 by 1 minus x by root 5 minus 1 by 2, right? And then minus, this will be, again, if I divide by root 5 plus 1 by 2, this will be 1 by 1 plus x by root 5 plus 1 by 2, right? Now, if I use geometric series, notice that here, I need to assume that the modulus of x is less than root 5 minus 1 by 2 in this case, root 5 plus 1 by 2 in this case. And turns out I can make that assumption, right? Yeah, I can just make it that assumption, right? Because, I can take that number. I can just choose x to be that number. If I do that, this will be root 5, and then sum from n equals to 0 to infinity. This will be x, let me write it as 2 by root 5 minus 1 x to the power n, right? Minus sum from n equals to 0 to infinity. This will be negative 2 by root 5 plus 1 x to the power n, right? And yeah, so this was our this sum from n equals to 0 to infinity f n x to the power n. So this becomes sum from n equals to 0 to infinity f n x to the power n is sum from n equals to 0 to infinity, and then I can take this 1 by root 5 in, and this gives me 2 by root 5 minus 1 to the power n minus minus 2 by root 5 plus 1 to the power n, and then x to the power n, right? So now if I compare, I see that fn will just be 1 by root 5, 2 by root 5 minus 1 to the power n minus minus 2 by root 5 plus 1 to the power n, right? Now we see that it's different, and let's say if you wanna make it similar, right? How can we do that? So what you can do to make it look similar is, if we just multiply this by root 5 plus 1 by root 5 plus 1 to the power n minus, and this by 1 minus root 5 by 1 minus root 5 to the power n, right? Because that's how it was earlier, right? Yeah, so if we do that, what do we get here? So 1 by root 5. So this will now be root 5 plus 1 by 2, right? Because the denominator is 4, into by 4 is 2, and minus. Now this becomes, this is negative 4, right? So this is 1 minus root 5 by 2. So you see that either way, even by generating function, even though it looks different, but it's the same formula, right? So 1 by root 5, and this is 1 plus root 5 by 2 to the power n minus 1 minus root 5 by 2 to the power n. And that's our generating function. So in this video, we just did not find the generating function, but the fact that I can either go using just some series trying to find some generating function and then trying to compare coefficients. Even by a completely different approach, we are getting the same formula. Even by matrix, they're getting the same formula. And even from this simple recurrence, we are getting the same formula, right? And that's the beauty of maths, my boy, my girl, my boy, my guys, right? So yeah, that definitely shows the beauty of maths, and then how you can deal with things finding this generating function. This idea was awesome. And then just trying to factorize, trying to get in the same form and compare. All this maths is so beautiful, Some really precious piece of revelation. And yeah, this will be there for generations and generations, and with every new generations, there will be some people who will be inspired by it, and then who will love it, who will wanna work on it, and this will just get better and better and better, and we will be able to solve all the mysteries, all the phenomena, all different hidden things of the world. That's how math works, guys. Okay, so yeah, let me not talk a lot, but yeah, we saw that either way we get the same answer, and yeah, all of them are pretty cool, right? Yeah, so that's it, guys. Hope you enjoyed the video. Thanks for watching. If you love it, do so with your friends, and I look forward to seeing you in the upcoming videos too.